Hi, my name is Mitchell Collins. I'll be presenting the model and control design of a DC motor. This is for the Control Systems class of Spring 2017. I'll begin with an introduction to the DC motor. DC motors work on the basis of converting direct current electrical power into mechanical power through a shaft, and this is done through a rotary apparatus as you can see in the picture. One main advantage of a DC motor over AC motors is its ability to run at variable speeds. So a DC motor can produce the same torque at these various speeds, which allows it to be a very versatile piece of equipment and can be used in a wide array of applications. The speed of the motor can be controlled by adjusting the armature windings current. Here is a brief outline of the project in the order I'll be discussing it. First, I'll begin with the DC motor operation and the model of the system, which I'll explain further in depth. Then I'll advance to assumptions for the system parameters based on the specific motor I chose, as well as design requirements. Then I'll talk about the design of my feedback controller, and with this I chose a PID controller. This is done using the root locus editor. Then I'll discuss the evaluation of the final closed loop step response of the system to make sure it meets all requirements laid out in the design. A typical DC motor operates through the principle of electromagnetism. As you can see in the figure above, the anatomy of a DC motor includes the magnet, which is the stator, the rotating arm, the armature winding, brushes, commutators, bearings, and a shaft through which mechanical power is applied. A DC motor must have a DC current supply or an AC to DC converter for operation. The rotating armature is what is connected to the mechanical shaft and is what actually provides the mechanical power. Here is a model of the DC motor system. B applied is the input of the system. Omega T, or theta with S, is the output. Tau T is the torque of the system. And finally, K omega T is the viscous friction factor. Ts shows the transfer function for the DC motor system. This transfer function relates the input, which is applied voltage, to the output, which is angular velocity. The table in this slide shows the parameters of the motor I chose, which is a Baldor brand DC motor. For the moment of inertia, the value is 0.0009 kilograms meters squared. For the torque constant, the value is 0.007384 newton meters over ampere. The viscous friction constant was 0.00724 newton meters seconds. The resistance was 1.2284 ohms, and the inductance was about 0.00023 henry. The initial design requirements of the system are as follows. For the overshoot, less than 8% overshoot is required. The settling time is less than 0.6 seconds, and the desired steady state error is less than 0.5%. This figure from MATLAB shows the uncorrected open loop step response of the system. As you can see, the settling time was about half a second, the rise time was 0.27 seconds, and the steady state was 0.825. To get the DC motor system within the design requirements, I chose a PID controller. By adjusting this controller and compensator in the root locus editor, I was able to get these specs within the requirements. This figure from MATLAB shows the root locus editor. This coincided with the step response of the system. Adjustments were made on this to get the system within the requirements, as well as using the PID controller. This figure is also from MATLAB and shows the closed loop step response of the system after using the PID compensator for adjustments. The rise time was 0.01 seconds. The percent overshoot was only 6.44%. The settling time was 0.075 seconds. And since 1 minus the final value gives steady state error. With the final value being 1, steady state error is 0. This comparison table shows the initial design requirements versus the final data after the PID controller adjustment. For steady state error, less than 0.5% was needed. This is achieved with the final value of 0%. Settling time of 1.6 seconds. This is also achieved with final 0.0752 seconds. And the desired percent overshoot was less than 8%. This is also achieved with 6.44%. In conclusion, the system for the DC motor was modeled. MATLAB was used with the root locus editor, the open loop step response, the closed loop step response, as well as steady state analysis. Since the open loop step response showed results that do not fit in the design requirements, I used the PID controller to get these within the requirements. With this, the closed loop step response showed results that were within these design requirements. Therefore, the motor system was successfully designed.